general relativity, step by step. I've got the Riemann-Christoffel curvature tensor here, written with 4 downstairs indices, and I've evaluated it in a local inertial frame so I can forget about the Christoffel symbols. This beast here is quite a lot. It looks like it's got 4 to the power 4 equals 256 components, because each one of these indices can range across 0, 1, 2, 3. Because of the symmetry relations, it turns out that there's only 20 independent numbers available here. But that's still quite a lot to deal with. So quite often what you want to do is to have a summary of the Riemann-Christoffel tensor, and the way to do that is to calculate the Riemann-Christoffel curvature tensor, but contracted on the first and third index. So we sum over alpha and mu, and that's equal to r. What's left after the alpha and mu is summed over, we've got a beta and a nu term there. And this thing is called the Ricci tensor. And we'll see in subsequent screencasts that the Ricci tensor has got profound physical meaning, and also we need to understand the Ricci tensor in order to write down the Einstein field equations. And today what I'm going to do is to show that r, beta, nu, you see you tend to use the same letter r for the Riemann-Christoffel tensor and the Ricci tensor, and there's a curvature scalar as well, which is also called r. You distinguish it by the number of superscripts and subscripts. Today I'm going to show that the Ricci tensor is symmetric. Right, so I've got my equation here. I'm going to say what r beta nu is. So that's equal to a half g alpha mu times this thing here. G alpha nu, I'm just copying that down there, comma beta mu, plus g beta mu, copying from there, comma alpha nu, minus the 2 negative terms, g alpha mu beta nu minus g beta nu, comma alpha mu. And of course what I'm going to do is to subtract r nu beta, alpha mu times. So what was called beta is now called nu, g alpha. What was called beta is now called nu. What was called nu is now called beta. That nu turns to a beta. Nu mu plus g beta and nu. So that's nu mu comma alpha beta. Is that right? What was beta is now nu. What was nu is now beta. Minus g alpha mu comma nu beta minus g nu beta comma alpha mu. Okay, so look at this. I'm looking at the difference between these two things, and it better be equal to 0 because I'm trying to show that the Ricci tensor is in fact symmetric. But I can do a little bit of cancelling here to make my life a bit easier. That term and that term are the same because all I've done is change the order of differentiation, and the same here. But I've still got these terms here, and I'm wondering what to do with them. Well, I'm going to write them out again. R beta nu equals a half g alpha mu times g alpha nu beta mu, just copying from here, plus g beta mu alpha nu, minus r nu beta, which is a half g, I'm going to pinch in a little bit here because, yeah, alpha mu times g alpha beta comma nu mu, copying from here, plus g nu mu comma alpha beta. And it's not immediately obvious that things are going to cancel from this. It's this minus. I'll just write in minus that. Minus that. It's not immediately obvious that things are going to cancel. However, I'm going to make the observation that alpha and mu in this case are dummy indices. They are summed over because I'm repeating alpha here and here, and I'm repeating mu here and here. And I can call them what I like. And so what I'm going to do is to swap the identities of these guys over and just write, where I was writing mu, I'm going to write alpha. So I'm going to swap over alpha and mu. Mu alpha, that's now, see if I can do this. That was a beta, and that was an alpha. Swapping over alpha and mu. So there's a mu there which now turns into an alpha, and there's an alpha there which turns into a mu, and that was a beta. Well, now we've got this sort of cross dependence here, but then I remind myself that the metric tensor is in fact symmetric. So I can just scribble these guys out and write alpha mu, swapping them over again. Not by virtue of the variable swapping being the same, but by virtue of the fact that the metric tensor is symmetric. And so now the thing factorizes again. And I hope I can, oh yes, I can see it. I've gone through this a large number of times and it's easy to make mistakes, and so I want you to know that this is about the 4th or 5th attempt to show this cancellation here, and I got things wrong in the first 3 attempts. That cancels out with that. You'll see that I've done that there's 2 differences. We swapped the alpha and the nu over, but that's okay because the fundamental tensor is symmetric. And I've swapped beta and mu over to get from here to here, but that's okay because the order of differentiation doesn't matter because we are using ordinary differentiation, not covariant differentiation. And similarly, that term and that term cancel out as well, which is nice. So it equals 0. So just to summarize what we've done, R beta nu equals R, or well, I guess write it out exactly that what I've derived. R beta nu minus R nu beta equals 0. And now we use the comma goes to semicolon rule, and we observe that if it's 0 in one frame, it's 0 in every frame, and therefore the Ricci tensor is symmetric in every frame. In any set of coordinates, and that is a beautiful, beautiful finding, and decidedly non-trivial. We were using quite a number of deep properties of differentiation and the metric tensor together, all in one sort of splurge, to come out with this symmetry relationship here. I think that's really rather nice. So the Ricci tensor is symmetric. Not wonderful. Stop.